Hello, I welcome you all to this another interesting screencast where we're going to be solving this engineering mechanics problem, and it reads determine the product of inertia of the shaded area with respect to the x and the y axis. Use Simpson's rule to evaluate the integral. This problem is coming from the engineering mechanics statics textbook 13th edition by R.C. Hibbeler. Right. So we have been asked to find product of inertia of an area. This is also a geometric property, just like moment of inertia. Only that in this particular case we're dealing with a product of two axes, right? And one of the main use of this particular property is mainly for determining the maximum and the minimum moments of inertia of an area of a given area or shape, such as cross-section of a beam. So you want to know the maximum and the minimum moment, right? And this information is mainly used for designing structural and mechanical members such as beams, columns, and shafts, right? And the product of inertia of an area with respect to the x and y axis is defined as I sub x y equal to integral of x y dA. Okay, and the units that are used for product of inertia of an area are just the same as units for moment of inertia of an area, which are just units of length to the power 4. And for product of inertia, you're gonna have a negative product of inertia. You can have a positive product of inertia. We can also have a zero product of inertia of an area about the x and the y axis, or with respect to the x and the y axis. And let's specifically talk about zero product of inertia of an area. You will have a zero product of inertia of an area if either x or y is an axis of symmetry. Okay, if either x or y is an axis of symmetry, then you expect product of inertia of an area to be equal to be 0. Okay, and the reason why you have negative or positive, this mainly depends on dependent on the location. It's dependent on the location and the orientation of the coordinate axis. All right. So this is a brief summary about the product of inertia of an area. You can read more about its other uses. Okay. All right. Let's dive into this particular problem. So we have this is an exponential, right? And we have been asked to determine the product of inertia of an area. So we'll get a strip. We'll get a vertical strip like so. And we're always going to be using the parallel axis theorem for calculating this. So moment of product of inertia of an area I sub xy equal to ixc, which is yc. This is a product of inertia of an area about the centroidal axis plus dx dy times area, where dx is equal to the centroidal location, and then dy local centroidal location is equal to the local centroidal location. Alright, so we have this small strip which is dx and is cutting the curve at x comma y, and therefore this length here to this point is going to be x and this height is y, and this centroidal location, which is that one there, this centroidal location with respect to the x-axis, this one is y curled equal to y divided by 2, and its differential area dA is equal to this height y and this thickness dx, and the function itself is y is equal to 0.8 e to the power x to the power 2. Okay, so this e is a constant, right? Which is a 2.7 something, right? Okay, so there we go. Let's write the whole expression. So we have moment product of inertia ixy equal to ixc yc plus dx dy a, and since there is symmetry for this small strip, we have symmetry, okay, about this local centroidal, about this axis here, okay, where we have y over 2. So because of symmetry, you just expect symmetry in at least one axis. You expect this part here to be equal to 0, right? Okay, you expect that part to be equal to 0. Okay, so let's write this as a differential expression. So we'll have d ixy equal to, this is a 0 plus dx dy, then this one as a dA. We have our dA equal to what's our dA is y dx, and then we have our dx equal to just x, then we have our dy equal to y divided by 2, then replacing all those and integrating on all the sides, then we'll have product of inertia itself equal to integral dx we said is just x, and dy is just y over 2, and our dA we said is just y dx. So our y we said is equal to 0.8 ex to the 2. So we replace this value. Here, okay, and here, okay. So if you wrote this, it just becomes ixy is equal to integral along the x-axis integrating from 0 to 1, then this becomes x y squared divided by 2 dx, right? So let's move on to the other side. So what do we have? Let me just write this. We have got a lot of extra work for Simpsons. Let me wrap this. Okay, so if we wrote this, so this becomes ixy equal to integral from 0 to 1 of x, and once we replace that equation, that becomes 0.8 e to the power x squared, everything times 2 divided by 2 dx. And if we expanded that, then it becomes 0.8 squared, that's a 60.64 divided by 2. So this becomes a 0.32 x ne to the power 2x squared dx, right? Great. So ixy is equal to integral from 0 to 1 of 0.32 x and then e to the power 2x squared dx. So at this point, for this integral, we are going to use the Simpson's rule, which is an approximate technique for working out integrals that are a bit time consuming and difficult to work out analytically, right? And this is one of the integrals. And that's the reason why Simpson's method was recommended from the initial start. So we are going to employ Simpson's method to find an approximate solution for this. Okay, so what is Simpson's method? So now, using Simpson's rule, which is the integral of a given function from a to b, f of x dx is approximately equal to delta x divided by 3, and then we have functions f of x0 plus 4 x1, this is the expression for Simpson's rule, plus 2 f2, then plus then plus again f4 x n minus 1, and then plus just f x n, and we close. So if you've seen here, the first value of the function itself, f at x0, has no coefficient before it, but later on you have 4, then 2. So 4, 2, 4, 2 keeps on repeating depending on how many strips you've divided your area, because basically what you are doing is you've got the curve that you want to integrate, then you divide it in the number of areas. So depending on the number of areas that you've divided it, and they are supposed to be even, okay? The number of subdivisions are supposed to be even. All right, so 4, 2, 4, 2 keep on repeating, but the last value has also no coefficient, like you've seen in this particular case. All right. Okay, so that is the expression, and then we have our dx, this dx. What this dx simply means, so you can check out this method to just remind yourself. Our dx, delta x itself, is equal to b minus a divided by n, okay, where n is the subdivisions. You can call them the strips or subdivisions. Okay. The more the subdivisions, the better the solution becomes, or the higher the chances of the solution converging, right? So it's subdivisions of the function. This is the subdivision of the function, and it is an even number. This is very important. Okay, it is an even number. So in our case, a is equal to 0 and b is equal to 1. Okay, and then we've chosen n. The number of subdivisions we're going to choose at least is 10. Okay, 10 is better off. We cannot go more than that unless maybe you're using a software package. Again, the less the number of subdivisions, the course your result comes out. Okay, so but if the question is asked like this, I'm sure your exam or your test will mention the number of the value of n that you're supposed to work on or to use, because the more the number of subdivisions, or the higher the value of n, the more tedious the calculation become, right? So delta x therefore is going to be equal to we said is b minus a divided by n, which is equal to 1 minus 0 divided by 10, which is basically equal to 0.1. Okay, so if we are to draw this on the number line, what we mean basically is this. I need to draw it. So at this point here we have 0, then at the other point there we have 1. So we divide this into 10 subdivisions. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let 1 come there. So let me rub this side. Okay, so these subdivisions are 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are the subdivisions we are talking about. These ones are the subdivisions which are delta x. Okay, so this point becomes a 0.1. This is a 0.2. This is a 0.3. This is a 0.4. And this is a 0.5. This is a 0.6. This is a 0.7. This is a 0.8. And this is 0.9. So this is your x0. Okay, this is your x1. This is your x2. This is your x3. This is your x4. This is your x5, x6, x7, x8, x9, and then finally your x10. Okay, that's all. And then you fit that in your function. Your function we said is equal to the function. We said the integral itself. We have moment of inertia Ix, which is equal to integral from 0 to 1 of 0.32. Let me just write the function there. I'll write it later on. Let me just say the function of x dx, which is approximately equal to. So we start plugging in all those values. So we'll have delta 1 divided by 3. Okay. Then we have f of x0. Okay. x0 we said is 0. Okay. The function itself, the function is equal to what's the function? Let me write it here. Let me just get a space here. I write it here. So the function the function is equal to 0.32 x e to the power x squared. So that's the function. Okay, that's the function we are dealing with. So you start plugging in the values in there. Okay, then you have plus, and that's a 4 f of x1. Okay, plus 2 f of x2 plus what is it, 4 again, f of x3 plus 2 f of x4 plus 4 f of x5 plus 2 f of x6 plus 4 f of x7 plus 2 f of x8 and then plus 4 f of x9. Then the last one, it is just f of x10, okay, which is basically just a 1, right? So you'll be plugging in those values in there. So x0 we said is equal to 0, and so on and so forth. Okay, so you plug in those values, and once you've plugged in the values, then you are going to get an approximate solution which is equal to, once you've done so, you get something like a 0.75 we round it off to 8. All right, so that is what we find. Let me just write this stuff on top. Our dA, I write it there, y dx. Okay, so let me just write the summary of the solution here. So therefore, ixy is going to be equal to, approximately equal to 0.7568 meters to the power 4. Okay, so you can check out that, you can calculate it and check my work. All right, I think this is about it. We found the product of inertia of an area, which is one of the properties, like I said, that we use for determining the maximum and the minimum moment of inertia of an area of a given area or shape of such as a cross section of the beam. All right, so I hope the video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screencast.